All right, so we are going to talk today about radical functions. So on Tuesday of last week, we did square root functions, and a square root function meant it was any equation. So an equation has a what?
X.
Inequality.
No. An equation has a, what makes something an equation? It has an equal sign, right? So an equation has an equal sign. So a square root function is an equation that has a square root in it. As in this problem right here is a square root function because it is an equal sign and it has a square root in it. Today we're going to talk about radical expressions, which are basically like square root functions without the equal sign. So an expression means it has no equal sign, so we're not talking about solving for anything. We're talking about simplifying. So what we're going to talk about today are a couple ways to simplify radical expressions. So radical expressions, any expression that contains a radical sign. So remember that a radical sign is synonymous with square root. So it means the same thing. So that like little division bar with the check mark, that's a radical. Anything underneath the radical is called the radicand. All right, anything underneath. So for instance, in this expression, which is the radicand?
D. No, the D.
D. Okay, the D is the radicand because it's the one that's underneath the square root symbol. So it's what's underneath that square root sign. Okay, it can't. We're going to talk about that in a second. Okay, what about here? What's the radicand? 2 is the radicand. Okay, so 2 is the radicand because it's underneath the square root. 5 is a part of the expression. It's just not the radicand because it's not underneath the radical sign. Okay, so that just means here, what's the radicand? Yeah, the whole thing, right? The whole thing there is underneath the radical. Therefore, that's the stuff that we're concerned about when we're finding the Okay, think about the rewind, the domain. So when you're finding the domain, what are you concerned with? The radicand. Only the stuff that's under the radical. But that's just when you're finding the domain, right? And that's because the domain has to be greater than
0.
Why? Why does the domain, which is all the x values, why does it have to be bigger than 0? You don't want negatives. Why?
Because it's too hard. It's too much work. No solution.
What'd you get for number 2 on the rewind? No solution. How come?
Because you can't do negatives.
You cannot take the square root of a negative. Therefore, anything underneath the radical needs to be greater than 0. So that's why when you do the domain, you set up the inequality. In this case, it would be like 2GD is greater than or equal to 0. Okay, because it has to be greater than 0.
If an intention said find the radicand.
You would just name what's underneath in the house. Yeah. I probably won't ask you that. It's quite easy. I make all your tests. Even the EOC?
I thought you were talking about the final.
I did. I made the final too.
You made the finals? Oh, that's good.
Yay.
Okay.
That's so good.
All right. So we're going to talk today about how to simplify them. So when we talk about simplest form, the way that I contextualize this or put this in terms of something you might know is when we talk about simplifying a fraction. How do you simplify a fraction? Like if you had, Anthony, if you had something like 3/6, is that simplified? Or could you do something with it? Yeah, you can do something with it. What do we call doing something with it?
Simplifying it more.
We might say dividing by 3. That's more telling me what to do, right? Starts with an R. Reducing. We reduce fractions, right? So essentially, we're reducing fractions, and we do it, and a couple people said 3, divide by 3. You're reducing by the what? Why 3?
Because that's the common.
That's the greatest common factor. Perfect, Gabe. So that's the greatest common factor. So that's the thing that goes into both of them, but it's also the biggest thing that goes into both of them, right? So what we're talking about today is how to simplify radical expressions. And instead of simplifying by a GCF, what we're simplifying when we're doing a radical expression is we're simplifying by the greatest perfect square. So keep that in mind. So we're simplifying by the GPS, greatest perfect square. Okay? That's not a thing. You can write it down, but that's not if you Google GPS, it's going to come up with Google Maps, not actually greatest perfect square. But just if you're thinking about what to reduce by, that's what we're going to talk about. So here are some things that we need to do when we're simplifying. A simplest square root function or a radical expression has no perfect square factors other than 1. All right, that means it's reduced all the way. The radicand, so inside the radical, has no fractions. And what's this last one say, Brian?
There are no square roots in any denominator.
Okay, there are no square roots in any denominator, so you cannot have a square root in a denominator, and we'll talk about how to get rid of that in just a second. Alfonso.
Wait, it does have fractions. Because in the last slide it showed radicand.
Okay, so it says the radicand, which is underneath the radical, has no fractions. So where do you see one?
Oh no, at that.
It's underneath.
So why, you're looking at this one, right? So why does this not actually qualify?
Because it has a variable.
No? Victoria?
Not all.
It's not all underneath it. Okay, the whole fraction's not underneath it. It would not be simplified if it looked like this. Because now there's a fraction in the radicand. But here, the only thing in the radicand is d, which is not a fraction. Okay? So you can have a fraction. It just can't have a radical, like the radical sign can't be over the whole fraction. You'll see some, and we'll show you how to deal with them. Micah.
So essentially, the radicand is a part of the fraction.
Yes,
Like-
but not the whole fraction. Yes. So it's a part of the fraction, but not the whole. Okay, so take a look at these right here. And I'm going to write them down below. So what's the square root of 16? 4. Why? Because 4 times 4 equals 16. So if the square root of 16 is 4, what's the square root of x squared? X. Why?
Because x times x equals.
X times x gives you x squared. So if you were describing to somebody, when you take a square root, what are you looking for?
The greatest comes back.
Not necessarily.
What was it?
Like, where'd we get 4? Whatever multiplies times the same thing, itself, right? So 16 is 4, 25 is 5, 49 is 7, x squared is x, okay? Sometimes we would write this as x to the 1, all right? What about square root of x4?
X2.
Why x2, Gabe?
Because you divide it and you divide the 4.
You split it in half, right? Because what do you do with your exponents when you're multiplying? You combine them using no. Addition. Yeah. You combine them using addition. So to break this down, you basically just split it in half. Okay. So x4, the square root of that is x2. Because again, x2 times x2 gives me x4. Okay. What about x6? x3. Good. Because x3 times x3 gives me x6. What about x8?
Because you add the.
You add the exponents. So it's x6. Okay, I did it right here. So x3 times x3, you add the exponents, so it gives you x6. Because remember, x3 is really like x, 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 and this is x, x, x. So how many x's do I have? 6. That's why it's 6, x to the 6th. All right, you don't multiply them unless it's a power to a power, which will also be on your final. You're up.
Miss Brown, you're always supposed to, like, the answer should always be lower than the one.
Yeah, because you're splitting it in half. Yeah. So this one would be what?
4.
So these all work out really nicely because they're what? Whole numbers. And these are all what? Even numbers? Yeah, Gabe?
So 500 it would turn out to be 250.
250. Yeah, x to the 500 square root would turn out to be x to the 250.
But you always put x. Right?
Yeah, because the base doesn't go anywhere. That's if there's an x in the radicand. Here it's just a whole number. Okay, so then, yeah, what happens if you have like,
3. A decimal? No.
Yeah,
so we can't have a decimal.
So do you round the fraction?
So,
round it.
4 plus 5.
hang on, I don't want to round it. I can't have a decimal because naturally you want to say like x 2.5, right? We can't have that. It's got to be, we've got to simplify it to a whole number. So again, what do I do with my exponents to get, I add them? So could I break this down into 2 things?
Yes.
What?
2 plus 3.
So I could do like x to the 2 and x to the 3, because what's 2 plus 3? 5. So I can break that down. But this is a perfect square, right? Which gives me what? Just x1, right? So now that one's gone. but this one still isn't done. So instead of doing this, instead of 2 and 3, could I break it down to something else? 4 and x1. Then what happens with x4? x2. And then can I do anything with this? No, that one's done and I can't do anything with it. So we would say that's fully simplified. So now what we did here, again, is pulled out your GPS, your greatest perfect square. What was our greatest perfect square in this? x4. Whatever's left stays under the radicand because you can't simplify it anymore. All right? If it were a fraction, we would say it's fully reduced. It's done being reduced. Again, how come the x4 became x2?
Because you do it.
Yeah, divided by 2. Okay, so what if it were x7? What would you break that down to? You could do 4 and 3, but again, why 1 and 6
Because
instead?
you want to keep one the same.
You want one of them to be
Yeah.
1,
Always gonna say.
right? Because then it's already small. So then how do I break down x6? Perfect. X power 3, x radical 1. Do you need this one? No. I'm going to keep writing it, but you don't need it. Okay? We're going to do one more. Gabe?
251.5.
No, we can't have a decimal.
Oh, we can?
5.8.
So,
No solution.
502 to the 1.
X 502 and x1. Why 1?
So you can leave it the same.
I know that that's done. And how come you picked 502?
Because if you add
If you add them, you get 503. And 502 is what kind of number? Even. So that means you can divide it by, which gives you
251.
And 1.
an root 1. X radical x1. So that's your answer. That's as simple right here as it gets. All right, you won't see them this big. But I just want to illustrate that if you do see one that large, you always want to pick what 2 numbers? 1, and then the even number that's 1 less than that. Yeah, so it's basically just, that's going to be the biggest even number that goes into it, and then you need a 1 because it has to add up to what? Whatever that number is, 503. Yeah. Okay, so if they're even, they work really nicely. You don't have to do all this stuff. If they're odd, though, that's when you have to do this.
So what you're saying, you give us all evens?
No, I'm saying I'm probably not going to give you all evens. All right, so that whole mess is if it's a variable. But if it's just a number, the process doesn't change. So the process is still the same. We're breaking it down, but we're breaking it down into a perfect square and something else. So for instance, let's say we have 32. 32 is not a perfect square, right? 36 would be. If it were 36, it'd be easy. We'd be done. It's 6. 32 is not a perfect square. So I want to break it down. I want to break it down into what 2 things can I multiply to give me 32?
30.
Unfortunately, it's 8 and 4 would work. Okay. Anything else? 1 and 32 or 16 and 2. So these are my options. So 1 times 32 would give me 32. 4 times 8 gives me 32. 2 times 16 gives me 32. These are my options. I want to pick the one that has the greatest perfect square. So, does this first one help me? No, because neither of those are perfect squares. So I'm going to cross that one out. Are either of these perfect squares? 4 is, right? What's the square root of 4? 2. But is that the greatest one? No. So which one should I pick? Good. So I would say square root of 2, square root of 16. Now, what's the square root of 16? 4. So that goes outside the house. And then 2 stays inside the house because can you break it down anymore? No. Okay? So the answer would be 4 root 2. So your answer is 4 root 2. And that's a simplified radical form. So we say, you'll hear people say, what's a simplified radical? That's it, 4 root 2. Now, could you put that in your calculator and turn it into a decimal? Absolutely. But we're not here. The whole point is that we're not writing them as decimal. These are simplified radical forms. Okay? So what about 63. Is that a perfect square? No, it's not. So I want to break it down into a perfect square factor. So what are some of my options for 63? I can only think of two. 1 and 63 or 9 and 7. 1 and 63, does it help me? No. So 9 and 7 is what I want to use. Square root of 7. Which of those is a perfect square?
9.
So 9 becomes 3 where? Outside. And then 7 stays inside because can you break 7 down anymore? No. Okay? So 7's done. All right. So the first thing you're doing is trying to find a pair of what? Perfect square factors, or at least one of them needs to be a perfect square, right? So I want a pair of perfect square factors. This one is the biggest perfect square factor that's going to go into it, which is why you want to do it. Could you have done this one using 4 and 8? Yes. I'm going to show you how. So I would take 32, and I would break it down to square root of 4, square root of 8, and I would have said 2 root 8. But then I would have had to realize that, well, I can break that down more to square root of 4, square root of 2, because what's 4 times 2? 8. So then I would say 2 times 2 root 2, which gives me 4 root 2, which is the right answer. But again, it's like saying I've got 200 over 300. What could you reduce these by? You could reduce them by 2, or you could reduce them by 100, which would be more efficient. 100. Because then in the first step, I get 2 over 3. Okay? So it's not wrong. It's just way less efficient to do it this way. So that's why I make a list of all my factors, because then I can look at this and see, oh, I definitely want to pick that pair. Okay? All right. Take a look at A. What's going on in A? It's a... The radicand has a fraction. So what can I do with it?
Divided by...
Divided by 2. I can reduce the fraction, right? So if I divide that by 2, what does it give me on top? 1 over 36, which now 36 is a perfect square. What's the square root of 1? 1. What's the square root of 36? So now, do I have any more fractions? Not a radicand anyway. So that one's simplified. So that, Alfonso, is what you would have to do. Okay? So if there's a fraction in your radicand, you have to simplify it so it's no longer in there. All right? What about B?
So don't you do it like...
I just do it, right? What's 3 squared?
9.
What's 4 squared?
16.
What's 9 plus 16?
3 plus 4, 7.
9 plus 16?
25.
25. What's the square root of 25?
5.
There we go.
All
right. So when you are simplifying these radical expressions, when you're simplifying, you simplify within the radicand as if it's in parentheses. So look at it like this is inside parentheses. Do everything you can and see if you can simplify it further. Okay? So down here, this is a what? It is a trinomial. What kind of trinomial? It's inside a radicand, or it's a radical. It's a radicand trinomial, I guess. It's a quadratic trinomial, which means we can probably do what with it? Split it into 2. What gives me x squared? What gives me 16 that adds up to 8? 4 and 4. Now, what do you notice about these two things? They're the same, so the square root of them would probably be what?
2,
No.
X plus 4 squared.
Stop.
X equals...
Take off the squared.
X plus 4.
All right. Because you're asking yourself, what times what gives me this? Well, this times itself gives me this, so the square root is x plus 4. Good. All right, we're not going to see many like that. Okay. All right, so the last little piece before you guys do a bit of practice. No, actually, I think you're ready. Try these. Now, before you go to your boards, some of these are like half done for you. So they took square root of 72. They already found the GPS factoring for you in this first one. Here they did half of it and they left it blank, so you would have to fill in that blank. So what would fill in this blank to give you 300? Good. Okay, here they did none of it for you, and here they did none of it for you. Okay, remember, if it's a radical with an exponent and a variable, the exponent has to be what kind of number? Even. It has to be even. If it's odd, you have to break it down. Okay, all right, go try them. Okay, so when you are talking about, I guess you can go then. All right, so when we are talking about radicals, we also have radicals like this, where the radicand is a fraction, but I can't reduce 5 over 9, right?
No.
That's not a fraction I can reduce. So instead of writing it as a fraction like this, you can say square root of 5 over square root of 9. Now, can you simplify either of those? Yes? Yeah, so square root of 5, can that one simplify? No, so it's just 5. And then 9 is 3, because 9 is a what? Perfect square. 5 isn't, so we just leave 5 alone. 5 is fully simplified. I can't break it down at all, I just leave it alone. So this is my answer, and this one's fine, because if you remember, the only rule is that you can't have a radical where? In the bottom. So it's fine if you have one on the top, you just can't have it in the bottom. Okay? Now, this one over here. So I can't reduce. So I've got square root of A5 over square root of 81A. So
9 and then the...
okay, I definitely can take out a 9 on the bottom, right? Because square root of 81 is 9. And then what do I have left in my radical? A? Okay. Can I break this down?
No. Oh, yeah, you can if you do the...
To radical A4, radical A1. What's this one? A1. So, yes, why? Because they're identical. So they cross out. So then all I'm left with is what on the bottom?
9.
And what's the square root of a to the 4th?
4.
A squared.
A2. All right, so I actually got rid of all my radicals there.
Wait, what happened to A5?
A5 became A4, A1. Because what's 4 plus 1? 5. Good. So then the A1s went away because they were the same. And then A4 became A2 because what's the square root of 4? 2. You split it in half. Okay, now, what if we had over here... Are either of these perfect squares? No. So right now, can I leave it like this? No, I can't, because I can't have a radical on the bottom. So I somehow need to get rid of that radical. But, Micah?
I was going to say just get rid of it and have it where it's like the whole fraction is a radical.
Yeah, I can't do that either, though, because I can't have a fraction in my radicand. That was another one of my rules. What? Where are you getting 4 over 2? That would just be if I were like, that's like subtracting numbers, right? I can't do that.
4 and 1 and then 2 and
No, because they don't, that's if it's exponents, but these are just bases, so I can't do that. Okay, hang on. Run with me here. What's the square root of 16?
4.
So what if I had square root of 16 times square root of 16? Well, that gives me 4, and that gives me 4, which ends up giving me 16. So what happens when I multiply a radical times itself?
It gives you the same.
It basically gives me,
Oh, but without the radical.
gets rid of the radical sign. So if I multiply a radical times itself, it essentially just does what to my radical sign? Takes it away. So if I need to get rid of this radical sign, what I can multiply it by
3.
not 3, but
Radical 3.
radical 3. But if I multiply by radical 3 on the bottom, what do I have to do on the top? Radical 3. Okay, so then radical 3 times radical 3 gives me just regular 3, right? And then on the top, what's 5 times 3?
15.
15. So this gives me radical 15. Now, can I leave it? Yes, because where's the radical?
On the top.
Do I care?
Yeah.
Nope, go ahead. We can leave it, right? I don't need it on the bottom. So how do you get rid of a radical on the bottom?
If you multiply
by itself. And then you have to do the same thing on the top because it's a fraction. So here, 5 over root 2, how would I get rid of this root 2? Times root 2 over root 2. What happens on the bottom? Regular 2, right? And then what about the top?
Radical 10.
No.
5 radical 2.
Yes. Why, Micah?
I don't know.
All right. She's right, but why? Victoria? It doesn't necessarily switch.
Is it because
Brian?
They're different. You cannot like. I'm gonna put
They're the
it.
same term.
Well, what was
It's
what?
not a perfect square.
Ashley?
Because one's under the
One's in the house, one's outside the house. So the 5 has to stay outside of the house. The 2 stays in the
So
house.
you can't even multiply those.
So nope, just leave them like that. Okay. But up here, why could we do it?
Because they're both radicals.
Both in the radical. The both radicands. Both in the radical. Good. All right. Nice job, guys. All right. I'll take a second. It's a lot of notes. All right. Okay. So let's take a look at, we're just going to take a look at one of these. Let's take a look at 15. So we have square root of 21b squared, square root of 25c4. So on the bottom it's going to be
25.
5
C2.
c2. How come that whole radical is gone?
Because
They were, say it again. They were both perfect squares. Exactly. So that one's gone. What about the top?
21.
Is 21 a perfect square?
No.
So can I do anything with it? Can I even simplify it to a perfect square?
It's okay. Just leave.
So 21 I'm just going to leave. What about the b squared?
Yeah, just 21B.
Turn it to B.
Turn it to b and then it goes where?
To the outside.
Outside the house. So b root 21. Because the b squared, what's the square root of b squared? B. And when you take the square root, where does it move?
To the outside.
Outside. All right, and then 21 stays under because did it have a perfect square factor? No. The only factors are 3 and 7, which are not
If we were
perfect
to have,
squares.
Like, let's say we're 16B.
Then absolutely, it'd be 4b.
4B.
Yep, perfect. Yes, you're up.
Miss Barrett, on that one, you don't do 5 on top, like on the top and bottom. Like you don't multiply by 5. You know how you to get the radical?
No, because what if 25 is already a what?
A perfect.
Perfect square. So I can take the square root of it. So I don't need to like get rid of it because I can already take the square root of it.
Oh, okay.
All right. We that went very quickly today. All right, so on your exit ticket, I would like you to do. No, hang on. I want you to do the ones I circle. So 1A, 1B, 2B, and
3C.
try 3A. Try 3A. Okay, go do those 4 at your seats.